So basically, we will start with the self-inductance. I just want to start like this. So when I have an arrangement like this, where I have a coil, and that coil supports me certain current. Now, what is that I am doing with that coil is I'm just changing the current in the same coil. For example, you have a coil like this. Imagine that this is a coil. Say, for example, N is equal to 1 turn. In fact, current enters and leaves. That is not your headache. It enters and leaves. Now, what is happening over here? I'll explain. Now, as the current pass through this coil, as long as it is steady, there is no issue. Now, what if I increases or decreases? Anyone in the class? What happens when I increase the current or decrease the current? No one is answering. ఆదిత్య ఏమవుతుందిరా కరెంట్ పెంచితే?
ఫీల్డ్ ఇంక్రీజ్ అవుద్ది.
కాదు, ఫ్లక్స్ ఇంక్రీజ్ అవుతుంది. దిస్ రిజల్ట్స్ increase of flux with respect to coil. Remember, flux is changing with respect to coil due to the change of current in the same coil. Now tell me what happens. What happens? No one? Please try to understand. This will increase of flux with respect to coil. So change of flux is happening. Now what is happening? An EMF is induced in the same coil. Due to change of flux. And this phenomenon is called self-induction. Remember, till last week, there is some external source of magnetic field, like a magnet, a current carrying coil, etc., like kind of thing, that will change the flux linked with your coil. Entire last week, we worked on this principle. Whereas now, I am discussing about change of flux due to change of current in the same coil. And this phenomena is what we will call as self-induction. So self-induction implies in EMF is induced in the same coil due to change of current in the same coil. See how the way you represented resistance as a property, this property also we need to represent it symbolically. And that symbol is like this. Remember, not spring. Spring-like structure. This is called inductor. This is called an inductor. Resistor, inductor. Inductance is a property. Inductor is the name of the element. Resistance is the property. Resistor is the name of that the element. Right. Now try to see how to understand this. The flux linked with this coil is proportional to current passing through the coil. More is the current, more high is the flux. And this constant of proportionality is replaced with a constant L. And this constant is called coefficient of self-inductance. That is called coefficient of self-inductance. And this is later stage you will call it as inductance. So you are representing this one means it is L. It is how you should represent L. How the way you are representing R, you will represent now L. L is literally flux by current. Flux Weber by ampere. And this has another unit called Henry. So therefore, hereafter we will represent it in terms of capital H. We will represent in terms of capital H. Right. Capital H is the unit. Henry or capital H. No issues. Any doubt? You ask me now, don't hesitate. Lock me here itself. Madhukar చెప్పు క్లాస్ లో ఉన్నా. Right. Now this is how you will represent. Remember, L is a constant. This is a constant for a given coil. For a given coil. This is where you call it coefficient of self-inductance or self-inductance, makes no difference. Now, when certain current is passing through the inductor, we'll call this as L, and this point is A, and this point is B. You know, the EMF induced in this is minus d phi by dt, which means minus L di by dt. EMF is minus d phi by dt minus L di by dt. The induced current or this induced EMF induces in such a way so as to oppose the change that produced it. Don't forget Lenz's law. Now I will take up this arrangement. I'll take up this arrangement. I'll take up in 3 different situations. Remember the first situation. First situation, I have a steady current. In case of steady current, di by dt is 0. So therefore, an inductor behaves like a conductor, AB. I'm assuming ideal conditions where the inductor has no resistance. In this case, VA is the same as VB. Remember, for steady current, this inductor behaves like a conductor. First observation. Second observation, di by dt is positive, means current wishes to grow. So the induced EMF induces in such a way so as to oppose this. To oppose this, the induced EMF need to take this polarity, A, B. Don't forget, I'm applying Lenz's law. The induced EMF, why? Because this is the direction of the current. So to stop this current, this is how it should take. So therefore, VA minus VB in that case becomes plus L di by dt. Next, suppose di by dt is negative. In that case, the induced current induces in such a way so as to oppose the change. If it wishes to grow, it won't allow it to grow. If it wishes to fall, it won't allow it to fall. That is how it behaves. That is the reason why it is called inertia in electricity. Inductance is similar to inertia in mechanics. In mechanics, inertia, it won't allow the body to come to state of rest from state of motion. Similarly, state of rest to state of motion, vice versa, whatever it is. It won't allow. So in this case, if this is A and this is B, if this is the current, VA minus VB is L minus L modulus. Remember, modulus of di by dt. Why I should write modulus? Already I have placed a minus sign here. When I placed a minus sign here, if we are representing it normally, minus of minus becomes a plus, and this will take a form like this. Now, whatever that I have written on this board, it's a very, very crucial step. Now, tell me, have you understood this or not? Without this, I will not go further. Say, I'm posting last week videos every time in YouTube for your understanding. Any doubt, ask me. Aditya, any doubt? Have you understood the basic?
No, sir. Yes, sir, I understood.
Right. Next. Geetika, have you understood?
Yes, sir.
Palvita, have you understood?
Yes, sir.
Nidhi,
Yes, sir.
వీడు కనిపించట్లేదు ఇవాళ. దర్శన్, మహంత్.
Yes, sir, understood.
Right. Now remember, it is this criteria upon which we are discussing all these things. Upon which what we are discussing. Next thing, what I would like to suggest you is, we will now step into application part of this. Now, we will now step into application part of this. And don't forget, I just want to mention again, inductance is similar to inertia property in mechanics. Next. In fact, inductor is an important element. Inductor is an important element in electric circuits. For example, I'll try to give you a simple model, example model. What is that? You have an arrangement like this. And you have a current di by dt is plus 1 ampere per second. The resistance is 10 ohm and inductance is 1 millihenry and 1 millihenry. Now, 1 minute. It is very high actually. I should write 1 into 10 power 3 ampere per second. And at that instant, charge is 10 microcoulomb and the capacity is 1 microfarad. Now, what is the potential drop across the arrangement AB? Now, you will call this as a B, you will call this as a C. Say, I have given all the data. At that instant, I is 1 amp. That's what given. Right. No issues. VA minus VB, I will write it as current into resistance, and that is 10 volt. VB minus VC is L di by dt. 1 into 10 power minus 3. di by dt 1 into 10 power 3. 1 volt. VC minus VB is Q by C. Plus minus. 10 microcoulomb by 1 microfarad, which is 10 volt. So VA minus VB is sum of these three terms. 10 plus 1 plus 10. 21 volt. Arya, if you have any doubt, ask me right now. Try to please see that. Do not compromise. If you are compromising now, you will repent for that later. Don't never compromise on such things. Learn elementary part properly. Learn always elementary part properly. If you compromise, what will happen? You will substitute one equation instead of other. And that's what my problem is. So do not compromise. Ask me whatever the doubt you have comfortably. Right. Still open to you. Do you have any doubt on any of these questions? If you have doubt, ask me. I've just introduced what is what are the areas that you are required to focus and all such things. So I've just introduced inductance for you. We will work on this later on comfortably. What is what and all that we will work on comfortably. But first of all, you need to confirm me, have you understood the property of inductance clearly? If not, it is very difficult for me to go further and handle it. I've just given you very fundamental approach. Right. The next thing that we need to learn is, okay, understood the basics. So the next thing what we need to understand is how to determine the self-inductance of certain elements. Basically, the elements involved ideal solenoid. So what I am discussing right now is self-inductance of a solenoid. Right. Now, what is a solenoid basically? You already know this. Just want to draw the diagram clearly. Now, this is the solenoid diagram. You know, long solenoid. We are dealing an ideal solenoid. Actually, I should rather use the word ideal solenoid. We know almost field is uniform in this. So what is the flux? Remember, flux is B into pi r square. The flux is mu naught number of turns per unit length into current into pi r square. Remember, you know what is this? Flux linked per turn. So what is the total flux? N times such a, because what is that I have applied is the lines inside the solenoid, but all these lines pass through every turn of the solenoid. Means every turn of the solenoid will affect because of the change of this flux. So every turn acts as a source. So therefore, the total effect increases by n. If there are n cells connected in series, the effective EMF is Ne. Same thing I am writing here. So what is that I am going to write is mu naught n square by L pi r square times I. So therefore, the coefficient of self-inductance is likewise. This is about number of turns. Suppose if you want in terms of this, both numerator and denominator, you multiply with the L, this one, this term. In that case, you will get mu naught n square pi r square. Remember, when I am writing this, in this is air-cored solenoid. That is air-cored solenoid. Suppose if it is something else, medium, in that case, L is mu naught mu r n square pi r square. That's how you will write. Okay. So one thing that you need to understand is, it is depending on geometrical factors. And medium inside the core. Two factors, mu r and this factor, right? So any student having doubt on this part of the derivation, please ask me. Any student in this class, if you have any doubt, please ask me. Any doubt? Remember, you are not supposed to use this all the time. When you are allowed to use this relation only on one condition. What is that? It is tightly wound solenoid. Tightly wound solenoid only you are supposed to use this relation. Why? Because if it is not tightly wound solenoid, this won't be the expression for B inside. Right. Right. Any doubt in this? Please ask me right now. Boys and girls. Next factor is, we are moving on to the next factor. That factor is, are you have a doubt unte adagante. Sahasra, do you have any doubt in this part? In the derivation part? Because mains lo adugutu untaru దీన్ని. They will keep questioning this in mains. Right. Right. The next aspect is, this is called transient currents actually. The heading for this is transient currents. ఉమేష్ చెప్పు. ఒక్క నిమిషం. ఫైవ్. ఇందులో కేటగిరీస్ ఏమైనా దొరుకుతాయేమో చూడు ఒకసారి. కేటగిరీస్ ఏమైనా దొరుకుతాయేమో ట్రై చేయాలి. దానిలో జాయిన్ చేయి. రైట్. ఓకే. Right. Transient currents. See, please try to understand. This is R and this is L. You have a key here. And this is a battery of EMF E. Now you close it. Actually, the current starts from 0 and it takes some time to grow. Let the drop across the resistor is V1 and the drop across inductor is V2 immediately after closing the key. Let the current be I. So simply what you will write is IR plus L di by dt is E. I have applied Kirchhoff voltage law in the loop. First question, any doubt on this? Bhagavat, do you have any doubt on this question, on this step?
No, sir.
Right. Mahant,
Sir, no, sir.
Right. Palvita, do you have any doubt?
No, sir.
రైట్ పల్విత మన ఫ్రెండ్ ఒక అమ్మాయి రావడం లేదు, నేను పేరు మర్చిపోయాను. స్కూల్ అమ్మాయి, మన నారాయణ స్కూల్ అమ్మాయి. అమ్మాయి పేరు మర్చిపోయాను నేను. ఎవరైనా హెల్ప్ చేయకూడదు గుర్తు చేయడానికి? గీతిక.
Sanjana, no, sir.
సంజన, వేర్ ఈస్ షీ? షీ ఈజ్ నాట్ కమింగ్. Sanjana is not at all coming. Right. Next. Now, yeah, by the way, in this situation, you will have IR. You can write this as okay. This is what we have. Let this be equation 1. Now you take equation 1 and try to do the integration part. Tanish, try to do the integration part. So what is happening? When I am doing the integration part, you should allow me to write the limits properly. E minus IR is equal to dt by L. When t is equal to 0, current is 0. At some time t, let the current be I. So this is 1 by minus R natural logarithm of E minus IR by E minus 0 is equal to T by L. So log E 1 minus IR by E is equal to minus T by L by R. With this I can write 1 minus. See, let us try to write some constants here. A different color I will use for this. Wherever I use E by R, I will use a term called I naught. Wherever I use L by R, I will use a term called tau. This is called time constant because ratio wise the same. L by R will have the same dimensions as that of the time. That's the reason. Now this allows me to write 1 minus I by I naught is e to the power of minus t by tau. This you can write it as I naught 1 minus e to the power of minus t by tau. Please try to understand that is the graph for current at any instant. Now if I plot current versus time graph, I'll get a graph like this. That's how you'll get the graph. Remember, This is corresponding to the maximum current, I naught. After a long time. Remember, when I becomes I naught, inductor becomes conductor, which means at that state the circuit looks like this. R conductor and cell, such that I naught is E by R. Remember, at steady state, this is called steady state. At steady state, you can say that an inductor becomes conductor. That's the picture. Are we clear? Anyone? Anjani, have you followed? Sahasra? సౌమ్య క్లాసెస్ రావట్లేదా? రైట్. Right. See, at steady state, it will behave as if like a conductor. And one more important point, I can see some more observations also. If you ask me what is VL, potential drop across the inductor, I can see the potential drop across the inductor as simply L di by dt, which is nothing but what is di by dt from this? What is di by dt from this? You can write di by dt from this is yeah, di by dt, L di by dt is nothing but E minus IR. E minus E by R times R 1 minus E power minus T by tau. So VL is clearly RR cancel. E minus E times 1 minus E to the power of T by tau. This can be written as E to the power of minus T by tau. So across the inductor, you can see that x-axis, y-axis, potential drop across the inductor versus time. You know, the graph behaves like this. That's how the graph behaves. At infinite, initially VL is equal to E, finally 0. The graph will tends to 0 finally. Okay? And not only that, another important observation. At any time, power delivered to inductor is simply current through inductor and the potential drop across the inductor. I naught 1 minus e power t by tau into VL e power minus t by tau. Good. I naught is E by R. So E square by R times e power minus t by tau minus e to the power of 2t by tau. This is the expression for power delivered to the inductor at any instant. Okay. Now try to please understand if you plot a graph for this. If you plot a graph for this, it looks like this. Because I require some Desmos. అదైతే కొంచెం నీట్గా గీస్తుంది మనం బాగా గీయం. The graph looks like this. It's placed here. I'll draw otherwise. You know, the graph looks like this. I've tried my level best to draw this approximately. I've tried my level best, but see, let us see. Right. So it reached a peak. So dPL by dt is 0 there. So now this entire thing depends on the fraction, this part. By doing the differentiation, minus 1 by tau times e to the power of minus t by tau plus 2 by tau times e power minus t by tau into e to the power of minus t by tau is equal to 0. So in this, cancel this. So finally, e to the power of t by tau is 2. At t is tau times natural logarithm of 2. It happens. At this instant, what happens is power delivered is maximum. Power delivered is PL is maximum. Remember, all these things in mains, they will ask as questions. If you remember this condition, your problem is done. That's it. So my point is very clear. You should be very cautious in doing such models. Right. Next aspect, the power graph also I have done. PL versus T graph. All that I have done. Also, please note that while a current I passing through this, the potential drop across the inductor is L di by dt. Power dropped across inductor is VL into IL. Voltage into current. Which means this is a rate of doing work. L I di by dt. Or the dw part can be written as a di. Now do the integration. 0 to steady current. The total work done is W is half Li naught square. Whatever the work that I am doing on the inductor. And this is stored in the inductor as a form of magnetic field energy, which means in the inductor, the energy is stored as magnetic field energy once a steady state current is achieved. Meanwhile, also there, even when there is a small current, it is stored in the form of magnetic field. How the way in a capacitor energy stored is in the form of electric field, in an inductor the energy stored is in the form of magnetic field. Now the question is, any doubts? Again, I'm asking you, do you have any doubts on this? More high is the time constant, more slower is the rate of flow of current. For example, to reach what you call 0.63 times the current, you will take one time constant. In one time constant, nearly it will reach as 0.63 times of I naught. Okay, right. Any doubt, please ask me. Boys, Sahasra, any doubt?
No, sir.
Darshan, do you have any doubt? Mahan?
Sir,
Yes.
Sir.
Bhagwat, ask me.
సార్ లిమిట్స్ ఐ నాట్ స్టడీ కరెంట్ ఎందుకు అక్కడి వరకు ఎందుకు తీసుకున్నారు సార్ ఐ నాట్
Bhagwat,
స్టడీ
my best question is, inductor lo, do you have the current more than I naught? Tell me.
నో సార్ బట్ ఇట్ ఈస్ నాట్ కాన్స్టెంట్ సార్
Who said it is not constant? I do accept it is not constant. Sometime between 0 to t, 0 to 10 tau, 0 to 50 tau. I have applied for full. If suppose if your intention is not to apply for I naught, right? Okay, no issues. You apply some I. In that case, work is half Li square. Till that time, the current is high, the energy stored is half Li square. Is that okay for you?
Sir.
And steady state, it is half Li naught square. Okay. Any doubts, boys? Right. So all this comes under growth case. Transient current, growth case. Now we will deal with decay of current case. What is the meaning of decay of current? Right. This is K2 and this is K1. Now, initially, K1 is closed and K2 is open. And I naught steady current is passing through inductor. What is your problem? My problem is all of a sudden open K1 and close K2. Now what happens? This is the circuit above. That's the current. That is how the current flows. And remember what all the energy stored in the inductor that is lost across the resistor. In other words, simply minus L di by dt will now become IR. Minus di by I becomes dt by L by R or dt by tau. Now you do integration both the sides. T0 current is I naught. At some time t, let the current be I. You know what happens? Minus of log E I by I naught is T by tau. Implies I is equal to I naught T by tau. This is the expression for decay of current in the inductor. Now what is going to be the graph? The graph follows. The graph follows. I naught and time t. That is how the current falls. Everything, even potential drop also same situation. What is VL? L di by dt, and which is nothing but minus L di by dt, in fact, IR otherwise. So even you will face the same situation. I naught R e to the power of minus t by tau, which means the graph for the drop of potential drop across inductor or resistor, whatever it is, that is also like this only graph. Okay, so it is a simple case, decay case, right? And there is a power all the time it is losing, all the time whatever it is given out to resistor, it gets heated, right? Now,
Sir.
please tell me, do you have any doubt in this part?
Sir.
Decay of current part. Any student?
Sir,
Yeah, please ask me.
sir, how are the potentials same, sir? Like,
Array, very simple question. Let we call this as A. Let we call this as B. Let we call this as C. VA minus VB plus VB minus VC is equal to 0. Closed path. So minus L di by dt plus IR is equal to 0. That's what I have taken. So whatever the drop across inductor, it is the same across the resistor. Only thing polarity changes. Yes or no? This situation is represented like this. Like this. So minus L di by dt magnitude plus IR is equal to 0. Now you tell me, is it true or not?
yes, sir.
Right. Next, please go through. You have any doubt, please ask me. Right. This is about decay of current. Anything you have, please ask me right now. Boys and girls. Next. Now we will take a complicated LR circuit. Remember, I am duplicating everything what I have taught you in RC circuits. I think you are not following that actually. I'll deal it bit later otherwise. Series and parallel combination of inductors is also required, but right now, okay, fine. I'll deal it series and parallel next class. Let this concept be completed. I have an arrangement like this. I have an arrangement like this. That's a simple circuit. Go through that. Now you see in such a circuits, how to handle. In such a circuits, how to handle. Now what they will inform is, the switch in the circuit is switch in the circuit is closed at t is equal to 0. I taught you in capacitors the same thing how to handle. Now also I am training you the same. Don't go for laborious steps. Step 1. Step 1. T is equal to 0 circuit. At t is equal to 0, inductor becomes a conductor. You know that. What will happen? Right. This is some R naught. This is a 2 ohms, which is R2. And this is 2 ohms. And remember, this is 1 ohm. In this case, this is 6 volts. Finally, 2 parallel 1 ohm. 1 ohm series. So therefore, the drop across this is going to be 3 volts. Remember, at t is equal to 0, 3 volts. And at t is equal to 0, I just done one mistake. Want to correct this. I've just done one blunder. Let me correct this. At t is equal to 0 circuit, remove the inductor. Remove the inductor branch. Why? Because at t is equal to 0, it acts as an infinite open resistor. So therefore, what is going to happen? R1 is equal to 2 ohm. R0 is equal to 1 ohm. This is 6 volts. Therefore, the current through this at t is equal to 0 is simply 6 by 3, 2 amps. The 2 amps. So the drop across the inductor, array inductor is nothing but here in this case AB. This is A and this is B. The drop across this is 2 into 2, 4 volt. That is step 1, t is equal to 0 circuit. Next, step 2. T tends to infinite circuit. At t tends to infinite, inductor becomes a conductor. So now what is going to happen in that? So this is 2 ohms. This is 2 ohms. This is 1 ohm. 2 parallel 1 ohm. 1 ohm series. 6 volts. So basically 3 amps will go like this. Gus, you said this is 1 ohm and all together is 1 ohm. Total is 2 ohm. 6 volts source. 6 by 2, 3. So it goes as 1.5 amps. 1.5 amps. So therefore, what to understand? What to understand here? Maximum current through L is 1.5 amps. Step 1, step 2. Last step I am doing now. Step 3. R effective determination. For R effective determination, this is a 2 ohm. This is a 2 ohm. This is R effective. This is 1 ohm. That's the picture. Remove the battery with its internal resistance. Remove battery with internal resistance. Remove the battery with its internal resistance. Now you need to find R effective. Can you please help me in writing R effective? R effective is 1 and 2 parallel, and that combination 2 ohms is series. 2 plus 1 into 2 by 1 plus 2, 3. 6 plus 2, 8 by 3 ohm. Sir, what is that you are doing? You have drawn 3 circuits. Hold on. Now I will conclude. So I will see the inductor circuit like this. Now I have my own formula. IL is I naught 1 minus e to the power of t by tau. This is my general formula. Now I will give you all this in one shot. You know, I naught means maximum current through the inductor. Can you please help me? What is the maximum current through the inductor? What is the maximum current through the inductor? I have given. Everything is on the board. Nidhi, what is the maximum current through the inductor?
Sir, I know.
What is the maximum current through the inductor, Nidhi? Oh my goodness. Everything is on the board. Mahant, what is the maximum current through the inductor? Mahant is not there. Bhagavat, what is the
Sir,
maximum current through the inductor?
1.5, sir.
How? I have shown this in step 2.
Yes, sir.
This is the step I have written, 1.5. How to find tau? Tau is nothing but L by R effective. Tau is nothing but 0.1 by 8 by 3. This is nothing but 0.3 by 8. So you just keep this aside, no issues. T by tau. Now I have given current through the inductor. At any time you can use this formula. Sir, what is that you would like to inform us? Yes. Remember, this is IL at any time. This is I at any time. This is I minus IL at any time. That's all. You can find anything from this. How do I find anything from this? Simple. Now you take this loop rule here. What is the loop rule here? 2 times IL plus, okay, what is the potential drop across this? L DIL by dt minus I minus IL times 2 is equal to 0. You can find anything from this. Because I know IL. So this will become minus of minus plus 4IL plus LDIL by dt minus 2I is equal to 0. Right. With this I can write, yeah, come.
ఒకసారి స్టెప్ 3 మళ్ళీ చెప్తారా సార్?
స్టెప్ 3లో నేను చేసింది ఏమీ లేదు. బ్యాటరీని ఇంటర్నల్ రెసిస్టెన్స్ ఇక్కడైతే లేదు, ఇట్స్ ఐడియల్ బ్యాటరీ. అక్రాస్ ద ఇండక్టర్ ఎఫెక్టివ్ రెసిస్టెన్స్ ఎంత ఉందో కట్టాను. ఎందుకంటే టౌ అంటే ఆల్వేస్ L/R ఎఫెక్టివ్. సేమ్ మెథడ్ ఆర్సీ సర్క్యూట్స్లో చేసాం. ఇప్పుడు ప్రాబ్లం ఏంటంటే ఆర్సీ సర్క్యూట్ జరిగేటప్పుడు క్లాసులు వెళ్ళాలి నేను, సరిగా వెళ్ళా. ఆర్సీ సర్క్యూట్స్ క్లాసులు వెళ్ళా సరిగ్గా. తర్వాత ఇదే చూడండి, మీరు ఎలా పాడైపోతున్నారంటానికి దిస్ ఇస్ వన్ ఇండికేషన్. అప్పుడు కూడా ఇలానే చెప్తాం మనం. T=0 ఎలా హ్యాండిల్ చేస్తాం. T= సర్క్యూట్ ఏమి ఇస్తుందంటే మ్యాక్సిమం పొటెన్షియల్ డ్రాప్ అక్రాస్ ద ఇండక్టర్ ఇస్తుంది. T= ఇన్ఫైనైట్ సర్క్యూట్ మ్యాక్సిమం కరెంట్ త్రూ ద ఇండక్టర్ ఇస్తుంది. జనరల్ ఫార్ములా ఫర్ ఐఎల్ ఏంటి గ్రోత్ కేసులో ఇప్పుడే డెరైవ్ చేశారు. I0 × 1 - e⁻ t/τ. I0 మ్యాక్సిమం కరెంట్, టౌ L/R ఎఫెక్టివ్. దట్స్ ఆల్. మహంత్, క్లియర్?
Yes, sir.
Now 4 times 1.5, 4 times 1.5, 6 into 1 - e⁻t/τ plus L 0.1 DIL by dt. 1.5 into minus of minus plus 1/τ. Tau is 0.3/8 into e⁻t/τ minus 2I is equal to 0. Hold on, ఓపిక్గా చేయాలి ఇది. రైట్. 1 minute. 1 minute. This is 6 minus 6 times e⁻t/τ plus, జాగ్రత్తగా చూడండి, this will cancel as 1/3. This will cancel as 1/2. So totally this will become 4 times e⁻t/τ minus 2I is equal to 0. You know what I have done? 2I is equal to 6 minus 2 times e⁻t/τ implies I have now given you main current. If you know main current, you can find anything in this. So if a complicated circuit like this is given, like for a complicated circuit like this is given, how to handle is what I have trained you right now. If a complicated circuit like this is given, how to handle? I have totally focused on this part only.
Sir,
Still,
sir.
if you have any doubt, please ask me. No issues.
Sir,
Yes.
sir, instead of doing this much, we can simply add the potential difference and equate them now, sir.
Your choice.
We'll get the same
You
answer.
can do, you will get the same answer. Or if you want to do Kirchhoff law also, you go apply. But issue is that will kill full day for you.
No, sir. Like
That will kill
after
full day for
finding-
you. That is the reason why I have given you a simple technique for this. Okay? It is your choice. You can go in that way also, no issues.
Yes, sir.
Right. So this is the fundamentals, what I taught you today. So I just entered into the topic, and tomorrow, day after tomorrow, complete problems on this. So I'll send you the notes right now. Right. So I'll close the class.